to sort of pan-European, large geographic extents. And I want to sort of take you through a little bit of a journey in terms of the evolution in the thinking of how urban land use change modelling has evolved over the last couple of decades. I think it's probably fair to say that much of the modelling that we do today probably stems from about 15 or 20 years ago in terms of its initiation. And I want to look at in terms of time horizons for the present, for the near future, but also to look at some of the long-term projections, long-term scenarios of urban land use change going into the future. So I'm in the Isaac Newton Institute, so what can I do better than to start with a Cambridge mathematician in this talk? So I'm sure many of you are familiar with the work of John Conway and his very famous game of life. I'm sure most of you are fairly familiar with the mechanisms of that. It will become obvious in a moment why I'm introducing this to you. You'll see as I take you through this. For those of you who are not familiar with the game of life, I'll just quickly run through it because it is quite important to understand some of the context of what I'm going to go on to say later on in this talk. So the game of life is basically constructed out of a cellular space where all cells are the same. And those cells can have two states. They can be alive or they can be dead. And what determines whether those cells are alive or dead are a number of what are called transition rules. So those rules are basically determined by the number of similar cells within a neighborhood of the cell of interest. So basically you can transition through time steps. If I do that, we should just move through. You can see that animation. But what you get are patterns of change evolving because each of those changes happen simultaneously at each time step. So we get changes in the patterns of dead and alive cells due to these transition rules. So that's the basic game of life. And what that can do is it can produce really quite complex spatial patterns that would otherwise be quite difficult to interpret. And this is what a number of land use modelers started experimenting with probably about 20 years ago to see how one could use the transition approach based on the game of life to understand spatial changes in the distribution of different land use types. And in this particular example, what people found is that if you increase the survival rate of those cells by changing the transition rules, so you effectively give more permanence or resilience to the alive cells, then what you start doing, if I just transition through a few steps at a time, is you start creating these very complex patterns, which, as you can probably see, is cognizant of the types of patterns we see when we explore urban development. But the interesting thing about these patterns is these appear to be completely chaotic and random almost, but they're not, because what I showed you earlier is that the transition rules are entirely deterministic. So we have sets of deterministic rules that provide really complex outcomes, which are irreversible and difficult to predict. And this is a completely different way of thinking about the world, because a lot of what people have done previously in trying to understand land use change patterns is they've used remote sensing, for example, or they've looked at maps. So they've started with the pattern and they've tried to interpret the process that underpins the pattern that they observe. And what we know from this type of exercise is that's not really appropriate. We had all sorts of, there was 10 years ago, the idea of socializing the pixel, the idea that you could understand human processes within a given pixel on a remote sensing map simply by doing statistical analyses of the patterns that you observe. So what we need to do is to get away from that way of thinking and start to try to understand the basic rules of the game that determine the spatial patterns that we observe in the very complex world around us. And that's where a lot of urban land use modelling began. So again, this notion that we can observe these types of patterns in practice. So can we try and find out what are the rules that determine the rules of the game of urban development through time? So this is the first example I'm going to show you. I'm going to give you a few different examples of different types of urban models, again, different scales and different paradigms of modelling as well. I'm starting with the basic cellular automaton, which is what the game of life is. So this is quite old work now. I think it goes back to the sort of probably about 15 years ago. And this was an exercise. You can see how old it is, because actually this is the EU15 as was at the time, right? Well, we'll get on that subject. Anyway, so This was an exercise trying to look at the impact of socioeconomic change on future projections of urban land use. And it was done within the context of the climate change issue, trying to understand the contributions of different urban patterns to climate change through emissions of greenhouse gases and the use of energy. And these are the old scenarios. I don't know if any of you are familiar with the old IPCC Special Report on Emissions Scenarios, published about 2000, set of socioeconomic change trajectories. They were labelled very imaginatively A1, A2, B1 and B2, which obviously means a lot to most of you. I won't go into the details, but I'll just show you some of the patterns here. So the top left map is what's called the A1 scenario. So this is really a sort of laissez-faire economics world, no spatial planning policy. You just, people live, build wherever they want to, as opposed to the opposite end of the scale, B2, which is very much more constrained in terms of spatial planning policy. So what you see on this map, all these maps, the four different scenarios, you're seeing the change in urban areas that are projected up to the end of the 21st century in this particular case, using a basic cellular automaton. So again, we've just got two states here, as in the game of life. There's an urban cell and a non-urban cell, so very simple representation. But what we have to add to that, we've got basic transition rules that relate to the neighborhood functions in terms of proximity of other urban cells. So a little bit like the little animation I showed earlier, we get urban growth around existing centers of urban distribution. But we have to add a little bit more information into that. We can't just run that arbitrarily. So the other important issues here we have to consider are the population change. You know, more people means more houses, quite as simple as that. Economic growth, in this case it was represented with GDP, because the economy strongly influences how people build and where they want to live. So we need to factor in some of those issues. So what we're trying to do in this case is already introduce a multi-scalar approach. So we operate with the socioeconomic data on population GDP at the NUTS2 regional basis, which is at a higher level, and then we have underneath that a cellular grid where we actually look at the individual land use changes. And those simulations then project through time to the end of the century. And again, what we're trying to show with this analysis, so within each of the scenarios, population and GDP changes differently. So we've got this layer of, you know, some scenarios have a higher population growth, some scenarios have a higher economic growth, but also the spatial rules that we use, the neighborhood rules, are also strongly dependent upon the scenarios themselves. So, you know, we have things like differences in the development of the transport infrastructure affects accessibility. So we get very different outcome patterns. And what you can see is that the A1, the laissez-faire economic world scenario, gives you this sort of spread of urban development, urban sprawl type patterns in reality, compared to some of the other ones. In terms of climate change, obviously that's bad because you've got more transport going on, you're using more land for urban development, etc. So not good. Okay, and there's other examples of this. This is a study, slightly more complex cellular automata, which is used to model an individual city. This is Cincinnati in the United States. Again, a cellular automaton. The difference here is, whereas in the previous example we're looking at just two states, urban, non-urban, in this particular example there was an introduction of different urban functions or different classes of land use or land cover that were explored here. In order to do that, the transition rules related to the interactions between those different types of activities. So, for example, residential development would occur closer to roads because you have accessibility, for example, but it wouldn't occur close to an airport because of the push effects of airports. So you can develop these transition rules that take account for of the different relationships between those things. So the transition rules are going from something which is a little bit abstract into something that means something in the real world. So that's an example. And again, this simulation was a historic one, looking at the middle of the 19th century up to the 1960s, showing the growth and the co-evolution of transport networks and different patterns of urban land use. Okay, but the examples I've shown you so far, and this is where the science is moving in terms of trying to look at these sort of large-scale urban systems. The problem, what I showed you previously, is that they're basically geographic representations based on transition rules where you could try to introduce some sense of reality or realism into what those transition rules mean, but they're still ultimately a graphical manipulation of geographic space. So we need some way of actually getting to the heart of what's actually going on, and the heart of what's going on are the individual actors or agents in the system who are making decisions about where they want to live. So in this example, I'm just taking things a little bit forward in that I'm now going to be talking not about cellular automata, but a sort of offshoot of cellular automata called agent-based modeling or multi-agent modeling. I noticed both of those terms came up in the stakeholder survey a little bit earlier, that people are using these technologies. And in the land system science field, agent-based modeling is used increasingly. You'll hear one or two talks tomorrow as well, if you're here tomorrow, looking at agent-based modeling in rural environments as well. So in this case, great, I can choose, my study region is this region, so here we are in East Anglia. I'm going to show you some examples of how we've applied an agent-based model to look at residential household location choices, which affect, you know, the pressures on building stocks. The motivation for this work was really about exploring the increasing pressures in this region due to population growth, but particularly due to changing demographic profile, so an aging population. And an aging population, as I'll show you in a moment, has implications for where people want to live. And that's quite important that we factor that in terms of our modeling. The other interesting thing I think about this example is it's very much an empirically grounded model. There are very, very many agent-based models, very good models, that are theoretically based, often toy models. They don't necessarily relate to reality, but in this case, because we're looking at a real-world problem, we wanted to empirically ground this. So we're using the Office for National Statistics at an administrative unit level called the level lower super output areas, LSOAs, which basically are variable, but they have approximately about 1,500 people in one of these units, down to a minimum of about 1,000 people. So that gives you an idea. And in East Anglia, there's about almost 1,500 of these individual spatial units. They're fantastic because within those units, there's an enormous amount of data available on the properties of individual households. So in this particular model, we're looking at modeling as our agents a household rather than an individual person, which is often the case with many of these models. And what we did in this case, and I'll show you some of the results for this, what it looks like, we did a sort of combined PCA, principal components analysis, and cluster analysis to look at the spatial patterns of trends in choices of individual household agents in terms of their preferences for residential location. And it looks like this. I'm going to take you through this in a bit of detail, so don't worry if it looks a bit confusing and fuzzy at the moment. Just to take you around this slide. So the map in the middle is East Anglia. Each of the colours represents an individual LSOA, administrative unit. There are zooms to the 4 cities, so Cambridge down here, Peterborough, so Ipswich and Norwich. What we have in terms of, we've classified our agents, our household agents. Here we've got students, single people, couples with dependent children, that is single parent families, couples with non-dependent children, and retired people. All right, so that's the classification we used. And what we have here in this analysis is to show, right, let me start over this side. So the colours on the map refer to one of these 12 clusters, and each of those 12 clusters relates to, or dominated, they have a preponderance of different types of household agents within them. It doesn't mean that you don't have a distribution of agent types, but for example in cluster 6 there are more household 7, which is retired people, and then more 5, which is single parent families, right? So that particular unit on the map is dominated by those household types, right? That's what the statistics show us. And it's really interesting to analyse these patterns before I get onto the modelling side of it, just to see what actually comes out from some of this. So let's focus on Cambridge. Here we are, so we've got a nice black colour here. What's that black colour? Cluster 12. Cluster 12 is here, and that's dominated by 1, which is, yeah, you have to follow the pointer, which is students. So we have students in Cambridge. Wow, well done us. I think we got that right. Okay, that's the data, that's not us, that's the data. So that's really good, that's a nice one. But the other one we're really interested in is, okay, so what's this? If you look at the coastal, we're interested in this coastal pressure issue because it's a very sensitive area in environmental terms, also in terms of the geomorphology, erosion. So we've got these yellow colours all the way around the coast. Yeah, so what's that? Okay, the yellow is, what's that colour there? Is it number 4, cluster number 4, which we go down here. which is household number 7. We go down here, it's retired people. So retired people actually live along the coast. They're the dominant household type that's existing along there. So if you just flip back to what I was saying a little bit earlier, that's potentially significant. If we have an aging population, that's just going to put more pressure on the coastal zone in the absence of other factors, such as spatial planning, for example, put more pressure on those areas. So that's really quite critical. So if we know where the retired people like to go, and if we study this, we also find retired people in the suburbs of individual cities as well. It's not unusual. We find there's another interesting one, this grey zone here. Is probably within the commuting belt to London. You tend to get couples without dependent children, so probably young career people. Single parent families tend to live within town centres, although sometimes actually in rural areas, quite deep rural areas. So we've got this wonderful stratification of where our household agents are. So what we do in terms of the modelling then is to take those sets of rules that determine where people are located. We run that through a simple demographic model. So people are born, they form a couple, they have kids, they retire and sadly die. So we have a simple demographic model which looks at birth rates, death rates, etc. So we can change the age profiles, etc. But during the life cycles of those individual households, we can see where they have a preference for different geographic locations in terms of living. And we can use that to parameterize the model in terms of the rule base that will enable us to look at how the population starts shifting around the regional landscape in terms of where it wants to move. I won't show you the live animation for now. So we've got a model that will actually then start looking at the distribution. So what we could do, just to give you 1 or 2 results, so this is the actual distribution of household types, and this is the model simulation of those types. So we get a fairly good visually eyeballing this representation of those patterns. And again, this just shows the simulations over the near-term future of the changes in the count of individual households. So you can see the retired count actually increases because of the demographic changes within the model. Okay, so that's the sort of thing you can bring in lots of interesting ideas and sophistication into some of those things. I'm now going to zoom back out again. That was zooming into a region. I'm going to go back to the European scale. And much of what I've sort of shown previously is embedded in the sort of more modern versions of the initial pan-European modelling approach based on a cellular automata I showed you earlier. This is a model called the Regional Urban Growth Model, which is embedded within what's called the Dynamic Integrated Assessment Model. You hear a talk from Ian Holman, wherever he is, on this modelling tomorrow as well. In the broader sense, it's an integrated assessment model. But what we've been doing here again is to look at a different set of scenarios. So this is you may not be familiar with the shared socioeconomic pathways. This is the IPCC's new version of their scenarios. Okay, I won't get into the details, but what you can see, the comparison between the 2 graphs here is that this just looks at if you model the demographic impact on urban development. But actually what we also do, and you can see you get some very, very big differences if you also look at societal change. So the problem in what I showed you in the previous example is the behavior was hardwired by the statistics. And we had no sense of, well, what if married couples with dependent children change their preferences? We don't know how that will go because we're determined by the statistics that tell us what happened in the past, effectively, or what happens in the present. Where in this model, we're trying to explore through the scenarios as well how different societal preferences might affect the ways in which people make decisions about where they want to live. So we're looking particularly at preferences for urban services. Do people want to live in cities because there are schools, theatres, shops, etc.? Or do they want the green space of living in the countryside? And how might that change with sets of assumptions embedded within the different socioeconomic change trajectories? So we're trying to come up with these patterns of societal preference change as well as the basic demographic change and the population change. And as you can see, you just get very, very different simulated outcomes if you do that. Right, running out of time. And that just shows, I'm going to skip through this one, that again, the types of patterns that come out. The SSP5 here is a little bit like the A1 scenario I was showing you earlier, sort of laissez-faire. So you've got this massive urban sprawl that comes out from those simulations. Right, moving on. I just want to finish up with a couple of slides to pick up a really important point that I haven't really discussed a lot so far. And that's all about spatial planning. So if we're looking at the urban system, we cannot ignore the fact, particularly in a country like the UK, that spatial planning is a critical driver or inhibitor, perhaps, of urban growth. It's absolutely critical, and we need to be able to model that. That's the bottom line. And we don't do that very well. We don't model institutions as agents especially well in many of these types of models, and I think it's something we need to do better. This just shows how important it is. If you look at these zooms here, this is Belgium, this is the Netherlands, a little zoom here. Belgium, incredibly dispersed pattern of urban land use, that's the red colours. The Netherlands, very, very compact patterns, about the same population density in these two examples, right? Belgium, well, up until recently had more or less no land use planning policy whatsoever, and so people could just more or less build anywhere. It's quite interesting if you go to Belgium. If you go there in the summer, you see forests. If you go there in the winter, when the leaves are dropped off, you see cities. Right? It's really, really unusual. So people just build their houses anywhere. And so you can see how important it is in terms of the spatial outcomes that we're dealing with. So going back to, you'll love this diagram. I put that there just to excite you all. I'm going to spend the next 2 hours describing this. No, I'm not. This is going back to the East Anglia example, actually, and this is something we tried to initiate during that study, was to engage with stakeholders who were involved in the land use planning process to try to understand how that process unfolded, so we could build a model of it, right? And actually, this is a map built by the stakeholders through workshop processes to try and understand all the building blocks and the relationships within the spatial planning process just in East Anglia. And we had stakeholders there who are effectively the nodes in this network, local authorities, Natural England, Environment Agency, etc., etc. And we looked at trying to use the stakeholders' knowledge to build up this sort of functional relationship between them. The interesting thing was, there's nobody in the room out of all these stakeholders who actually knew how the whole system worked, right? And there were conversations going on of, oh, that's how it goes. Oh, I never knew that. Oh, that's interesting, yeah. So people were getting a lot from this. So actually what we've got is this really complex system that is a typical example of complex system in that there's no real command and control here. It's all sort of comes out from the interactions between the individual agents in the system. Right, so in true Peter Coxian style, we got away from that into the simple version, right? That's as simple as we could get it, which we're starting to use, or which we did start to use to build models of how that institutional process worked. Looking at categorizing the principal types of agents and the roles they have and the influences they have on other institutional agents within the system. And one of the things in my particular group we're trying to do a lot now is try and build more of these public policy, mostly institutional models, so we can start to do experiments on how public policy agents interact with landscapes, because they influence landscapes by pulling policy levers, introducing policies. They monitor what's happening and they respond to that. So it's an adaptive, responsive system that I think is really important that we start reflecting on how we model that in order to inform some of the policy process a little bit better. So just a few concluding remarks. There are lots of models out there across different geographic scales. Most of the urban models can focus on those key list of drivers I've got here. And my own prejudice, of course, is that I think moving towards the agent-based models gives us an enormous amount of wealth and richness in terms of modeling these types of complex processes, but we have a long way to go before we finally make more progress. Thank you very much.
Thank you. So again, have time for 2-3 questions.
To what extent do you nevertheless include statistical effects in your agency-based models, and how robust are the outcomes of your models against those? I mean, I'm not sure you're not slightly creating a false dichotomy. There is, within models, there is complexity, and there's complexity at a local level in terms of interactions, which you could capture in these agency-based models. But there's also a lot of uncertainty that you will never be able to capture within the model that may very well drive the positive behaviour of the outcome.
Yeah, absolutely. So, really good question, and it's a really pertinent one as well. We in many cases try to use data to parameterize and or calibrate the models. There's a lot of interest in the moment about using machine learning, for example, to calibrate agent-based models. You're always, of course, though, dependent on the data you've got. A lot of local landscape models will do social survey work, where we go and do interviews with, say, individual farmers and use that to build up behavioural profiles, which you can then turn into a rule base. All models are going to be constrained, if they are empirically grounded, they're going to be constrained by if the processes themselves that led to behaviours previously are going to change in the future at some point. And actually understanding that, I think, is absolutely critical in how we do this. I think all models suffer from that problem. I think the agency-based models are interesting because we could start to explore rules around adaptive learning. So actually the agents aren't static, they're not hardwired, they don't just do the same thing every time. They actually evolve their behaviour in responding to the environment itself. And that, if we can start moving towards that, I don't think we're anywhere near that, but if we can start moving in that direction, that gives us some really powerful tools to look at adaptation processes within landscapes.
John Brew next. Fascinating talk. I love the game of life analogy as well, and it's more advanced. Just on that point, think about quantifying uncertainty. Do you find stable and unstable states? And could we use that to help disentangle?
Yeah, we do. And we do a lot of testing with, particularly with the agent-based models, looking at stationarity and the sort of spin-up periods required to achieve that, and yeah, how stable they are. You might hear a bit more about this from my colleague just behind you, Callum Brown, who's talking about agent-based modelling tomorrow, may or may not be talking about some of those issues. Yeah, so I think you could do a lot of diagnostics, and actually, I didn't mean to be sort of rude about the sort of toy model approaches, but actually the more theoretical models are really, really interesting in trying to understand behaviour of systems away from, you know, the inconveniences of data, where you could do these sort of experiments just to learn how the system works and how it responds. So I think all that type of testing is really, really critical. Yeah.
So one final question.
You've shown in the last example with the planning that, so to speak, not all agents are created equal. So what's in general your perspective in the role of modeling power relations in this system?
Yeah, again, it goes a little bit to the similar question beforehand. You know, you can monitor, observe, collect data on the current landscape of agents, their behavioural profiles and their decision-making strategies. You can theorise about that. There's lots of decision theories out there in the social sciences that help you do this type of thing. But at the moment, we don't really know how individuals change their behaviour. And I think that is absolutely critical. And it may be that those agents respond in quite interesting ways to a changing environment. You know, you look at any social pressure, and it leads to a response. It leads to a change. And until we've actually observed that, it's very difficult to actually understand what that response will be. But I think experimenting on that and trying to explore what those responses might look like, I think is really, really critical. And I think that's why, again, where the agency approaches are really useful. Yeah.
So thank you, Mark. Please grab Mark over lunch if you have more questions. Thank you.